Good day everyone, you're welcome once again to Physics 210 class, which is the basic electronics class. This is study session 3 and we'll be taking inductors and transformers. Inductors and transformers. By the end of this session, you are expected to have been able to explain what an inductor and transformer is. You should be able to state the different types of inductors and transformers that we have. You should be able to state the types of inductor combinations that we also have in our circuit. Also, you should be able to explain the working principle of a typical transformer. You state the power rating as well. At the end of it all, you are expected to be able to solve basic questions on inductance and inductive reactance in AC and DC circuits. All these are the learning outcomes expected of us. Apart from this, you should be able to understand one or two things, some key important things that you'll be coming across during the course of this class. So let's pay attention, pick our pens to jot one or two things so as to understand this session well. Introduction. Inductors. So the first thing I'll be introducing to us is inductor. When we say inductors are coil-like structures that are found in electronic circuits. They are found in our electronic circuits just like every other component found in electronic circuits. They are used to carry specific functions. An inductor is a passive electronic component that stores energy in a magnetic field. Now you should be able to understand the function, that specific function of an inductor from this particular statement. In fact, there are two things you should be able to understand, you should be able to deduce from this particular statement. An inductor is a passive electronic component that stores energy. It stores energy in what form? In a magnetic field when electric current flows through it. It stores energy in a magnetic field when electric current flows through it, which means current needs to flow for it to store energy in a magnetic field. The energy stored is in form of a magnetic energy when electricity is applied to it. Remember that current can only flow when electricity is applied. So that is when electric current flows through it comes in. Electric current will only flow when the electricity is applied to it, and that is why it is said that energy stored is in form of magnetic energy when electricity is applied to it. Now, you see the symbol you are seeing here is an inductor symbol. Some people might be saying, but it wants to look like the resistor. No, it doesn't. You will see that this one looks like a spiral, a spiral shape. So it is the shape is different from the resistor shape. The resistor shape is just like the resistor symbol is just like a zigzag, but this is not a zigzag. This is like a spiral. So this is a symbol of an inductor. So if you see any the circuit diagram, if you see any circuit diagram and you come across this type of a symbol, this is an inductor symbol. Now, there are different types of inductors. I'll be taking, in fact, you might come across maybe one or two apart from these, but these are the major types of inductors. The first one here is air core inductor. You see this inductor, they are used when the amount of inductance required is low. Since there is no core, it is saying here that there is no core because it's just an air core. Air core. If you know what air means, it is not something you can hold. That is why it is saying here that since there is no core, it does not have a core loss. Since there is no core, then there will not be any loss in the core. It is used for high frequencies. Then this one says, the second one is iron powder inductors. Now in this type of inductor, the core is iron oxide. Iron oxide. They are formed by very fine and insulating particles. This particular inductors are formed by very fine and insulating particles of pure iron powder. And the iron powder we are talking about here is the iron oxide. High magnetic flux can be stored on it air gap due to the gap. Yes, it is used in power applications. Now you see this iron powder inductors, this statement I am making here, you might be asked that you should give the properties of different of these inductors. Properties, state the properties of iron powder inductor. So if you are being asked to state the properties of iron powder inductor, good, what will you just say? The first one, they are formed by very fine insulating particle of iron powder or pure iron powder. It has a core which is iron oxide. It has high magnetic flux that can be stored in it. It is used in power applications. You understand? I intentionally put this, they are just like properties of this particular inductor. But I put them there so that you will be able to at least write something about it if you are being asked. Normally I'm just supposed to highlight these different types of inductors for you, so you read them up, make research, check yourself online. But I'm intentionally stating all this here so that it will be easy for you to refer back to it. Then we have the ferrite core inductors. Ferrite core inductor, in this type of particular inductor, ferrite materials are used as the core. Just like in iron powder inductor, the iron oxide is used as the core. For air core inductor, there is no core because the core there is air. Now, so for ferrite core inductors, the inductor here, the ferrite material is used as the core. Now it says the general composition of ferrite is XFe2O4. That Fe is the ferrite and O is oxygen. So we move on.
So we have inductor voltage and current relationship. Now, you see the voltage across an inductor is directly proportional to the time rate of change of current through that inductor. Voltage across an inductor is directly proportional to the time rate of change of current through that inductor. And that is why we have VL, which is the voltage across that inductor. Remember, L stands for the inductance. So VL is proportional to the height T. Now, if we are now changing that proportionality sign, remember you need to introduce, if we are removing that proportional sign, we need to introduce a constant, which is called the proportionality constant, which is L. And that is why we now have our V equals to L, which is the constant introduced, the high, the T. Now, where our V is the voltage, which is the voltage across that inductor, then the L is the inductance. Always our inductance is in Henry, so you can see it in millihenry, microhenry, and all sorts of that. Then we have the rate of change of current to time, which is the high, the T. And so that is the first thing, that is the first relationship we have there. Then we can have another relationship. I didn't write this here, but I will explain it. So through my explanation, you should be able to get it. Now the second equation can come in this form. It's just trying to, work around this particular V equals to L, the height T that we already have. What do? You make the height to be alone, so that you will now be having the height, make the height the subject of the formula. So you'll be having the height equals to 1 over L V dt. That is what you'll be having. The height 1 over L V dt. Remember what you're having is the height. In mathematics, you want to eliminate that the height, then you introduce the integration sign. It's just like you want to remove square root, and you put square. Then you know that square root and the square root cancel each other. So the same thing applies to integration and differentiation. So we already have the height, which is differentiation. So you want to eliminate that to introduce that way, then your integral sign beside your the I and the D will eliminate each other. So you will now be left with I equals to 1 over L integral d dt. So that is what we do. So you can have those two equations. Both of them shows the relationship between inductor voltage and current. So both of them can be used, and you'll see more of them when you read up or go through materials that deals with inductor and transformer.
Inductor combinations. We have been dealing with different components since the first session. We discussed about the resistor, we have discussed about the conductor, and we are now discussing about the inductor, which is also part of the different components we see in our electronic circuit. Now for all these components we have been talking about, we have discussed how they are combined, or how they can be combined, or yes, how they are combined in circuit. And the two major combinations we have been discussing since, they are the parallel and the series combinations. Yes, you see these two particular combinations, they are just common for the three components we have been talking about. So in other combinations, these interconnections of inductor produce more complex network whose overall inductance is a combination of the individual inductors. Yes, that is talking about the total inductance there. Yes, the total inductance maybe for the series or for the parallel combinations. However, there are certain rules for connecting inductors in series or parallel, and these are based on the fact that no mutual inductance or magnetic coupling exists between the individual inductors. Now you see this particular statement, I want you to note it down, that no mutual inductance or magnetic coupling exists between the individual inductors. Note it down, this is another exercise. Add it to the exercise you are having now. You see, all these exercises I am giving to you, these will make up another part of your assessment for the semester. Remember that this particular what we are doing now is on elements. So all the assessment you'll be having for this semester will be on elements. So the physical assessment you'll be having are these ones that we are giving to you now through the class. So will make requests for all this. Now take note of this particular statement, that no mutual inductance or magnetic coupling exists between the individual inductors. Take note, you will have to explain to me what this statement means later on before the end of the semester. Now we move to series inductor. Remember we said it, that we have just series and we have parallel. So for series inductors now, when inductors are connected in series, the total inductance, that is the sum of all the inductances. No, yes, it's the sum. When we say total inductance, we know that we are talking about the sum of all the individual inductors, the inductances of those inductors. Now, how do we get the sum? Is it like the way we have been doing it for the resistor we do for this, or is it the way we did for conductors we will be doing for this? So let's move on and check. It says the definitive measure of inductance is the amount of voltage dropped across an inductor for a given rate of current change through it. Now this is just telling you the meaning of an inductance. What does an inductance mean? Inductance is the amount of voltage drop across an inductor for a given rate of current change through it. Now the inductors are connected in series when they are daisy chain in a straight line by connecting end to end. By now we all should know that when any component is connected in series, they are the end-to-end connections. They are the ones connected end to end, like on a straight line, joined together, having one leg attached to the other side of another one, having the second leg attached to the other side of another one. So in the series combination of inductances, in the series combination, inductances are added together. This is mainly because the number of coils turned are increased in the series combination. So this particular combination for inductor is just like the same thing we do for the resistor. Just the sum of all the inductances, that is what you are going to be having for the series here. Just like you have the sum of all resistors being added together to get the total, because to get the equivalent resistance then for your series combination of resistors. So the same thing applies here too. Hence the equivalent inductance of the series combination of the inductor is the addition of the individual inductances of the connected inductors.
So quickly, let's go through the circuit we're having here. We're having four inductors connected end to end. End to end connection shows that the series connection. So in series combination of an inductor, the same current flows. Just like I said earlier, the same current flows through all of them, but with different potential difference. By now we should know what potential difference means. So we have different potential difference, but the same current is flowing through. So here now, the potential difference here for each one of them, you make use of the current voltage relationship that we talked about earlier, which is V equals to L divided T. So what we are going to be doing here is that for inductors, each of the inductors, you need to get the voltage across each one of them. So to get the voltage across each one of them, you'll be having V1, which is voltage for the first inductance, equals to L1, that is the inductance of the first inductor behind T. So you do that for the second one, the third one, and the fourth one. So by the time you have each of the voltages that way, then you can now say the total voltage across, the total potential difference across the circuit will now be addition of the four of them. Now you add the four of them together. So by saying that the L1 divided T plus L2 divided T plus this divided T, remember that one thing is common, and that is divided T to all of them. So L1 plus L2 plus L3 plus L4, that is L equivalent. So L equivalent, that is addition of all the inductances of the inductors, that is L equivalent divided T. So you can have it as equation 1 the way it is that way, or you have it as equation 2 the way it is that way. So by the time you equate both together, you realize that in getting the total inductance or the equivalent inductance of a series inductor is just addition of all the individual inductances you are having in the circuit, which is L equivalent equals to L1 plus L2 plus L3 plus L4. Now we move on to parallel inductors. When inductors are connected in parallel, the total inductance is less than any one of the parallel inductances. Now if we go through the one we did just now for in the last slide for the series inductor, if give just say maybe your L1, the first inductance is 2 millihenry, and the second one maybe 3. Just give values for all those inductances and try to add them together. You realize you get a bigger value. But now for the parallel inductor, when inductors are connected in parallel, the inductances is the total inductance or the equivalent inductance is less than